Hello, welcome to Triple 117. Here we're going over Chapter 12 LaPlace Transforms. This is part 2 of our lecture series this week. So last time we talked about why we want to do LaPlace Transforms is basically going to a frequency domain versus doing everything in a time domain. Specifically when we're using AC sinusoidal sources with inductors and capacitors nearby, the second order differential equation gets really, really hard. It's actually easier to switch to the frequency domain, do our analysis there, and switch back to the time domain. So the Laplace transform is helping us switch to the frequency domain. Here is a proper Laplace transform in terms of like the mathematics is you get this cursive L, and in the brackets, the time function, we're going to swap to the frequency or Laplace function, capital F of S. All right, you can do that by integrating from 0 to infinity f of t e to the negative s t dt. Now, this isn't a math course, so I'm not going to sit here and do all the mathematics side by side with you, okay? You've probably seen this already in another math course anyway. Okay. But remember, the whole point is we're taking a time domain function and converting it to a frequency domain function. Okay. Now, in electrical engineering, there's a couple of common waveforms we typically see, and we could figure out the Laplace transforms of those and make kind of a cheat sheet for us to use called Laplace table. Okay. Typical waveforms are DC, flat voltages, sinusoidal, cosine-based AC voltage sources, so it's the standard trig functions. Exponential time decaying functions like an inductor bleeding out its energies. You have a decaying current. Step functions, which you talked about last time, which is a switching function, you switch on or off. And then a ramp function if we're ramping up a voltage. Okay. So how do we literally take each of those functions and then go through the integral, and then you'll come up with an answer here. Okay, now again, you could go do it on math you want, but this is as electrical engineers, all we care about is what comes in, what comes out, not the math in between. All right, that's why I have calculators to help us. So the standard functions we'll see are going to be an impulse function we talked about last time, right? Impulse of t is just 1. Okay, step function u of t is 1 over s. And remember, the variable s is the frequency variable. Okay, so what this means is step function u of t, if you do 1 over s, as frequency gets higher, this number gets smaller. Ramp function t is 1 over s squared. So as the frequency gets up, this ramp function exponentially gets smaller and smaller. Exponential e to the negative at is 1 over sa. Sine function is sine of, which is sine wt is omega over s squared plus omega squared. Well, omega is our initial cosine function or sine function. Remember, sine function, we have to put a specific frequency that the function works at. So this could be sine of 377t or cosine of 377t, whatever that frequency that the sine function is operating at, we just stick it as omega here and here. Okay. Cosine function, very similar, except as the s on top instead of omega. Damp ramp, so basically this is a ramp function that gets smaller and smaller as time goes on. We got 1 over s plus a squared, where a is the part of the rate of exponential decay. We have a dampening sine function. Basically, this is a sine function that starts big and then kind of envelopes smaller to 0. So think about a big sine function that just gets smaller and smaller, kind of like a cone that zooms in and eventually goes away. Okay, and that's omega over sa squared plus omega squared. Okay, and so basically you just literally use this chart and just do a hot swap between the functions. So if you have a sine function, literally just erase sine and just put this in. Okay. So quick example. Let's say we have a voltage source, a DC voltage source, and the time switches on at t equals 0. Okay. On the left-hand side, this is a time domain function. We could write it f of t equals 336 times u of t. U of t is our step function. Any DC or any constant in front can be taken apart to the side, because remember, this is integration. Remember, in integration, any just regular numbers can be slid outside the integration symbol. So our frequency domain or Laplace, after Laplace transform, our new voltage source is 336 divided by s. Okay, remember, u of t is 1 over s. That's the transform. We go back up here, see u of t is 1 over s. So you basically just hot swap it. and instead of lowercase f of t, you're capital F of s. Okay. So 336 times 1 over s, you can just multiply those three, you get 336 over s. So this is the right-hand side is what our circuit is going to look like in the frequency domain. The big difference between these two is notice the switch isn't there anymore. Right? In the frequency domain, it doesn't make sense to have a switch that turns on and off frequencies. Right? The frequency will be dictated by the source itself. Okay. So just think about the switch is getting absorbed into the voltage source as they divide by S. That's how I like to see it. Okay. So there is some, every device you can do this transform over. Okay. Now we just talked about there. We're going to make it official. Is when we're doing Laplace transforms, you get the actual straight transform of the time function, but what if they're added together? What if they're multiplied together, right? There's some kind of nuances on top of just having a number and having a function and do a direct conversion. Okay. The first most common one, what if there's a constant in front? Again, from previously, what if it's 336 volts times our switching function or a step function? You can always pull constants out of Laplace transforms because it's an integral. So the formal definition is in the Laplace transform of k times any time function, constant k can come out of the Laplace transform. So then so this k will be 336 times Laplace transform of u of t, and we know that's 1 over s. So this is a formal proof of you could take constants out. Okay. Now, what about addition and subtraction? All right. So let's say we have a time function that has three separate quantities. You have one function plus another one plus a third one. Remember last time we had a triangle waveform that went up, down, up. Those are three separate functions we added together, right? So here, what can we do if we add three functions together? Okay. We can split up the add subfunctions to individuals f1, f2, f3. And if you remember, integrals, when you have two functions added together inside the integrals, you can always split them apart to two separate integrals. Okay. So it's very easy as taking each individual function f1, f2, f3, find their individual Laplace transform for, so Laplace transform of f1 is capital F of s, Laplace transform of f2 of t is capital f2 of s, Laplace transform of f3 of t is equal to capital F3 of s. And then addition is, you could again always take you could separate addition out for Laplace transforms. So then Laplace transform of everything is just f1 of s plus f2 of s plus f3 of s. It's basically commutative property, if you remember that. You can always just split up addition and subtractions. Okay. So far it's pretty easy, right? This is all, it's like common mathematical sense. Okay. Now let's get to the kind of wonkier stuff. What about differentiation? So very often we have something dv over dt or di over dt. What happens here? Okay. So d over dt can always kind of get split up as d over dt of a particular voltage, current, or some variable. Okay. Now, for swapping it over to the frequency domain, the Laplace transform, all d over dt's can be taken out of the integral, out of the function, and multiplied by s. That's the equivalent. The d over dt in time domain is literally multiplied by s in the frequency domain. So for example, Laplace of df over dt would equal literally an s times f of s. So whatever this f of t is, you could do an individual transform and just put the derivative in front as multiplying an extra s into it. And because you're doing a derivative, you will have to look at initial conditions. Okay, so you might have some condition before we start the circuit that you need to add in here, right? But that's all integrals and derivatives. You got to find initial conditions, right? What is an initial condition? What if the capacitor is already charged before we observe the circuit? What if the capacitors or inductors pre-charged, right? This could have happened yesterday before you looked at it. If the capacitor is already charged, we don't have to charge it. That obviously changes the circuit parameters, right? So that extra voltage on the capacitor, we have to take into account. Otherwise, if we don't do that and this is 0, when we do our math and our circuit analysis, our answer will be as if the capacitor was empty. But if it's not empty and is fully charged, the actual current in the circuit will be vastly different from an empty capacitor versus a full capacitor. So initial condition just represents us pre-counting the capacitor full, which you need to, otherwise the math won't work out. Okay, and I'll show you how to get this. It's not that hard, right? You basically take the circuit at t equals 0, just literally do the circuit and the math of the circuit to see what the initial voltage is, and that's what the pre-charged capacitor is. Okay, we'll see it a few times. Okay, big takeaway here: d over dt is s. That's all you need to know. Okay, and I would say taking derivative of a cosine function can get kind of funky, or a derivative of an exponential cosine function gets a lot harder. Multiplying a function by s is a lot easier. I think we could all agree with that, right? And this is one of the big advantages of Laplace transforms is I'd rather multiply by s than look at derivative tables for exponential functions, right? Honestly, I never really like calculus that much. I know it's very important, but it's tedious, right? Well, what about the opposite of differentiation is integration? Integrate E0 to t of some function f of x dx, right? For example, this could be current. Integrate from 0 to t. How much voltage was on the inductor? Well, how long did we turn the current on? That's what integration means. So in terms of Laplace transforms, integrals are literally just divided by s. Okay, so for here, if we take the Laplace transform of an integral of a function f of x, we literally delete the integral and just multiply 1 over s. That represents the integral. And whatever function was inside the integral, we literally just forget about the integral and just only look at that function and do our Laplace transformation from the table. So basically, all this is literally the initial Laplace transform of the table and just put a divide by s extra, and you're done. Right? Again, integrating, it can be time consuming, especially if the function is complex. Just slap on divide by s is way quicker. I'd much rather do arithmetic than calculus any day of the week. I think we can all agree on that. Again, integration differentiation simplification is probably the main reason why people use Laplace transform. Right. Other thing that can get messy, time delays. Remember last time we talked about what if we want to delay that switching function u of t minus a? That's very common. So we have a time delay of a. In the Laplace transforms, in time and frequency domain, this is you slap on the e to the negative as. Where a is just the seconds. Like this could be like 5 seconds, 6 seconds, but s is a function of the frequency, so that needs to stay. So for example, if we have a function that got delayed by, let's say 3 seconds, a is 3. You have t minus 3, and then it turns on at t minus 3. So the whole circuit got delayed by 3 seconds. We would literally take the u of t minus 3. This u of t minus 3 gets transformed into e to the negative a of s. This is the exponential to a negative a of s. Multiplied by f of s, where f of s is the original function right here. Okay, that's all this means. So this u of t minus s literally gets swapped into e to the negative as. That's the big difference. Okay. In terms of the original function itself, it's just a straight conversion from the Laplace table. As you can see, there's a pattern. We're just trying to make things easier by taking the original function, splitting it off from this extra addition we're putting on, and just use a table for the original function and just make some extra rules for these extra add-ons like differential integrations or time delays. Okay. So remember we said a is 3. So specifically here, I would write e to the negative 3s. And that would signify a 3-second time delay. Okay. Now in the frequency domain, time delay kind of messes everything up because there is no time in frequency. So I guess some exponential represents it. Honestly, I don't know. I'm not a math person, so don't ask me. Okay, but I do know that transferring over e to the negative as represents a time delay. Okay. There's a couple more you could look in the textbooks. We have another table called the operations table. So this is multiplied by a constant. You can see K f of t is K f of s. Addition and subtraction means we could just do a straight conversion 1 by 1. Here's your derivative. df of t is s of fs minus our initial condition. You technically have a second order differential, which is d squared f of t, d squared f of t over dt squared. So it's a second order differential. You could follow the same logic here. Second derivative is s squared f of s minus s of the original initial condition. So s times whatever initial condition we figured out, minus the derivative of the initial condition, which could be 0, could be something else. Okay. And then technically you could do it for the nth level, but I've never seen anything over second derivative, honestly. Right. But this is how you would do a Laplace transform for higher order derivatives. Integrals, you have one integral, f of s, integral f of x is f of s over s. We just talked about that. You got your time delay here. You got some other things like translation, frequency, scaling, and so on, right? But honestly, the ones I have in blue are probably the most common ones you're going to see. But the idea is we have these in case, you need them. Okay? So 2 tables. Table 12.1 is the actual Laplace transform of the individual functions. Table 2 is how to take those functions and split them off their additions and just do mess around with the addition and then, or the extra stuff, and then mess around with the original function as well. So you're going to use both tables kind of side by side. Okay. And be honest, this stuff, this 12.2, you're probably going to end up memorizing more basic stuff. You probably won't even need this table. 12.1, the initial Laplace table, you probably need a lot more because some of them can get pretty complicated. Okay. Now, I talked a lot. Let's see it in action. Okay. You have a circuit here. Now, I know it looks strange, but you have a DC current source. Okay. Now, remember what a current source says. The current coming out of this line is literally IDC, and it's never going to change. Okay. Now, this is a weird switch, but it's here because it turns on the source. Now, one thing with a current source, you can't put a switch in series and turn it off because you're going to break the current source. What you do is if you put a switch in parallel and you close it, the current will loop infinitely within this section and nothing will go out to the circuit. So this is how you turn off a current source, is you put a switch in parallel and close it. So when it's closed, the current is always looping through the source and nothing is going to the rest of the circuit. You have this RL circuit, before t equals 0, the switch is closed in, there's 0 current flowing out here. Now at t equals 0, notice we open up the switch. As we open up the switch, the current will then go to the resistor and the inductor. And here you got to figure out what is the RL circuit response of this current turning on. So literally as t equals 0, the switch opens up and current flows into the resistor and the inductor. How do you do this? Well, in the time domain, the current coming out is I dc times u of t, and because the switch is here, we have that step function at t equals 0. This is equal to the current flowing through the resistor and the current flowing through an inductor, because this is one node. Okay. Now, for each individual component, we could figure out the voltage. So initially, let's say I want to find the voltage V of t across an inductor and a resistor. It's actually through the whole circuit, right? Well, each current we need to swap into voltage. Well, current swapping to voltage is very easy. That's Ohm's law, right? I is always equal to V over R, and I know R. That can be 10 ohms. So I can be swapped over to V over R. So that's Ohm's law, easy mode. Inductor gets a little trickier. Remember, the voltage across an inductor, is the current going through the inductor is represented by a voltage. And that voltage is 1 over L integral 0 to t Vx dx, right? Now remember, we want to find voltage, so we got to swap away from current into voltage. So we're doing this direct swap. So everything right here, this integral is the original current flowing through the inductor. And then IDC is constant and UT comes with us. Okay. Now, just looking at the second equation, it gets a lot messier because now you have an integral. And this is a first order differential equation, right? We can't solve this, but it takes a couple of steps. Now, I could do my Laplace transform of this circuit. Now, notice these two things are added together, so I can swap them apart. So I can literally take V of t over r and swap it over to V capital S of r. Because 1 over r is a constant, so that just goes with us. So this is an easy swap, easy Laplace transform. The middle one, 1 over L stays out because it's a constant. The integral is divided by S, and the voltage stays with us to capital V of S. Okay? And then IDC is a constant, so that stays with us, and then U over T is divided by S as well. So notice we took an integral and we swapped it over to now this bottom equation, which is a Laplace domain equation. This is just algebra, right? I want to find V of S. That's my answer. I know R, I know L, I know IDC. Those are part of the circuits. This is a pretty simple algebra equation to find V of S. You literally just put them V of S on one side. Okay. And just to show you how to do that is we have their Laplace transform equation, V over S over R plus 1 over L V of S times S equals IDC over S. Our goal, because I'm asking you for VS, is to put VS on one side and everything else on the other. Well, this is just basic algebra, but we'll go through at least one. What's common between these two equations, the red and the blue? It's the V of S. We could pull it out because of commutative property. So pull out V of S from both of the division signs. We get V of S, open bracket, 1 over R plus 1 over SL. Okay. And that's equal to IDCS on the other side. That just carried over. Now, I want to find V over S by itself. So this whole bracket will put in the other side by dividing both sides by this bracket. So swap it to the other side here. Down here, we have V of S is equal to IDC, which is this part carried over. The S is carried over. And this whole bracket is at the bottom now. Bracket 1 over R plus 1 over SL. Okay, just algebra. That's all we're doing. Let's put S into both of these. So let's get rid of the brackets, multiply S on both sides. You have S over R plus the S goes in here. So we have S over SL, the two S's cancel. So you just have an L right here. Okay, so now we have IDC divided by S over R plus 1 over L. It's good form to put the biggest S by itself. So we want to get rid of this divide by R. The easiest way is you multiply the top and the bottom by R. That's your, you know how the trick is you multiply by a special 1 to get rid of denominator stuff. So we're going to multiply up the top and the bottom by R. So then R into IDC is just R times IDC. R into S over R, the two R's cancel, so you have an S right here. And then 1 over L times R is you just have an R over L. Okay. So our answer for Laplace domain, or through the Laplace transform in the frequency domain, is V of S is equal to R times IDC over S plus R over L, where R, IDC, R, and L are known quantities of the circuit. And then we could just plug in S for a particular answer if we need it. Like we could say S of 6,000 hertz, or 3,000 hertz, or 4,000 hertz, and get a hard number. And that's the whole point of this. Okay. It's very good on the bottom to keep what we call in the root form. If you remember from like middle school, we talked about, you know, the roots of an equation, right? You remember that the FOIL and all that ax squared plus 2 ax squared plus 2b squared plus c and all that stuff, right? That's the type of roots we're trying to go to. So here, S plus A is a root where A can just be R over L or something. Okay. So it's just a common thing. We like to put everything in root form. Okay. So this is literally the answer to this circuit right here. Okay. Now, this is where we take our exercise. And we're going to do an RLC circuit. So it's the same circuit except a new capacitors here. So I'll tell you right now, the capacitor kind of makes it a lot more complicated. Here, the switch turns on. I want you to find a voltage, V of t, except just find V of s in the frequency domain. Remember, the current flown out is IDC times U of t, and it's going to split between three branches. You can have I of R plus I of L plus I of C. I already did the hard part about swapping it over, finding individual branch current. So you have V over R is your current through resistance. The current through an inductor is 1 over L integral 0 to t Vx to dx. So we just did that in the problem before, so you could just use it as a reference. You have this new value. Current through the capacitor is C times dV over dt, and IDC U of t follows with us. So I want you to take this equation right here, and I want you to do a Laplace transform. Remember the rules from table 1, the two tables we found. What happens in integral, what happens to the derivative. Do the Laplace transform and find a function similar to this. It's going to be more complicated because there's a capacitor now, okay? And then down here, I want you to take that function and put it into a cleaner root form where you have a V of s. So V of s will be something divided by a s squared plus something, okay? So go ahead, try your best shot. I'm kind of throwing you off in the deep end to see if we could push you, one level ahead of what we got. Okay, so let's go ahead and take our 20-minute break. We'll come back and I'll show you what to do, but give it a good shot and see how far you could get, okay? So we'll see you in a little bit. Good luck. Hello, welcome back to EEE 117, Chapter 12, Laplace Transforms, Part 2. So we're back from our 20-minute break for the exercise. So let's go ahead and see how to do everything. All right, so first, we have our time domain function, V of t over r plus 1 over L integral Vx to dx plus C dV dt is equal to IDC times step function U of t. We need to convert this with a Laplace transform because they're all added together. We could do each one by one. V over t over r is V over s over r, so it's a direct conversion. 1 over L carries with us. Integral is divided by s, and we just carry over to V over s. Now here's the new part. Capacitor, C goes with it because that's a constant. D over dt is multiplied by s, and then V over t turns into capital V over s. And then IDC is constant, that comes over, and U of t is 1 over s, which is then means IDC is divided by s. So this is a Laplace transform. We're done. After this, all you gotta do is just some basic arithmetic to make it look nicer. Remember, I want V of s, so everything should be equal to V of s in some form or fashion. So if all this addition, the common thing V of s can be brought out. So V of s is equal to, open bracket, 1 over r plus 1 over SL plus C over s. C times s is equal to IDC over s. So we're already kind of singling out V of s. And come over here, we just take this big bracket and flip it to the other side. So we divide both sides. So now V over s is equal to IDC divided by s times all the bracket stuff. 1 over r plus 1 over SL plus C times s. So first thing we do is let's multiply s in to see what we got. We got IDC over s over r plus 1 over L, because the s goes, so the s goes into 1 over s. So that's just s over r. S goes into 1 over SL, so the s on top and the s on the bottom both cancel. So you have 1 over r. And s goes into c times s, so the s is double up to s squared times c. Now remember, we typically want to get this in quadratic form where s squared is by itself alone. So we could just divide by 1 over c on both the top and the bottom to cancel out the c right here. So we 1 divided by c on the top is IDC divided by c. So we have 1 over c times IDC. And then we'll go through each one. The c times s squared, 1 over c, the two c's cancel. So we have s squared right here. And then the other s in the bottom equation is here. We have s over r. So we said s over r times 1 over c. So we get s times 1 over rc, right? So 1 over c times 1 over r is 1 over rc. And lastly, we have 1 over L times 1 over C, which is 1 over LC. Okay, so this is our final form we need. It's a quadratic form. Remember, quadratic form is typically s squared plus a constant times s plus a second constant. Okay, and this is how you would write the Laplace, the frequency domain equation to finding out the voltage. Now remember, IDC is known from the circuit. It'd be like 10 amps. C could be like 10 millifarads, R could be, I don't know, 50 ohms, and L could be 1 millihenry. So all these will hard crunch the numbers, and you'll just be left with S squared plus something times S plus another number. Okay. So that's pretty much how you do circuit analysis in the general form here. Now the question is, we have this big equation. What do we do with it afterwards? After we put numbers in it, where there's two things we can do. Number one, we could stay in Laplace domain and finish our analysis, saying this is my function of voltage. I could then put S in as a frequency variable, and just literally remember that table we had of 1,000 hertz, 2,000 hertz, 3,000 hertz, 4,000 hertz. You can literally plug in S as a frequency and figure out what happens. Right, that's a viable thing to do. Right, we could design and modify the circuit based on frequency domain standards. Right, so we can either make a circuit based compare to outputs. We could stay in the frequency domain and build our circuit and analyze anything we want. Right, and again, in all honesty, in power systems, we talked about phasors nonstop. When we do phasor analysis, we stay in the frequency domain. We don't do time domain analysis in power systems. We do literally only frequency domain analysis, which is called phasors, right? Or if you really need to, quite rare, but you might need to go back to the time domain. So here we have to take this giant equation and do an inverse Laplace transform to go back to the original V of t. Now we already know the answer. If I take the inverse Laplace transform of this, I should get this original equation up here. Right? Because it transforms, if you transform from the time domain to frequency domain, and then you go backwards, it should be always equal. Okay. Now, of course, this is circuit analysis course. I just need to show you the method of doing inverse Laplace transform. I'm not going to go into detail, but it's something you should learn. So the first step in doing any inverse Laplace transform is taking whatever frequency domain function you have, and you have to divide it into roots. You remember we had to keep this in quadratic form. The reasoning why is because you need to split the quadratic form into S plus A times another S plus B, where A and B are roots. Okay. Remember that quadratic formula that you had to learn in what, middle school? All right, B squared, something B squared. I can't remember. It's like 2AC plus or minus square root B squared, or 2A plus or minus square root of B squared minus 2AC or something like this, right? I can't remember, all over 2A, right? It's that type of calculations you need to do, okay? Now, once you have your roots, then you ask yourself, there's 4 types of roots you can get based on your quadratic formula. It could be distinct real roots where there's no imaginary numbers here, and they're different numbers. A and B are different. Okay. This could be like S plus 4 times S plus 10. They could be distinct complex roots where it could be S plus 3 plus J4 times S plus 3 minus J4. Okay. They are different roots. They're conjugates because you'll still have the same A's on both sides and same B's on both sides. It won't be plus, it won't be minus. Okay. You could have a third one called repeated real roots where you have the same roots twice. S plus 3 times S plus 3 is S plus 3 squared. And in a very rare case, you can have repeated complex roots where it's just regular complex root, except you have 2 copies of each. Okay. Whichever one you use, there's 4 distinct, whichever answer you get, they'll always fall into one of these 4 categories. Okay. And then you could go to each one. So, for example, distinct real roots, this is kind of an example of a more complex root system. Okay, so you have a root to the third order because you have S. So S by itself, the root is 0 because it's technically S plus 0. Then you have an S plus 8, so the root is S is negative 8. Then you have a root of S plus 6, so the root is negative 6. So you have 3 roots in the bottom. It doesn't matter what's on top, it's just what's on the bottom. Okay. Now, what you're supposed to do is you're supposed to take this big function, split them up into individual roots. You have some constant divided by S, plus another constant divided by S plus 8, plus another constant divided by S plus 6. There is a way you can split these denominators apart. And this is called partial fraction decomposition. probably scared you with that name, but you should have learned this in calculus or early differential equation. It's a way to take a complex equation with lots of roots and split them apart. Okay. So there's a lot of cancellation and a bunch of rule steps of assigning k values and setting things to 0 and whatnot. I'm not going to go over it because we don't have time, but go back in your calculus book and relook partial fraction decomposition, or realistically just use a computer simulation to do it for you. Well, whatever happens, this original f of s function, 96, s plus 5, s plus 12, blah, 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 the end result is you'll have 3 separate roots. In this case, it's 120 over s minus 72 over s plus 8 plus 48 over s plus 6. Okay, these two are perfectly equivalent statements. We just did a lot of algebra to split them apart. Okay. The reason why we need the second function is we could do an inverse Laplace transform. Now look at an inverse Laplace transform of this giant mess. You cannot do this straight because there's no rules of splitting up multiplication. But because we set this to the second group where you have everything split up between addition and subtraction, we can easily do an inverse Laplace transform of 120 over s. 120 over s is that 1 over s is the u of t. Okay, right here. 72 over s plus 8, or negative 72 over s plus 8 is a negative 78. I think that's a typo. That should be a 72. It's a negative 72 e to negative at. And remember, 1 over s plus 8 is e to negative at times u of t. So the u of t gets split out here. And lastly, you have a positive 48, 1 over s plus 6. That should 48 times e to the negative 6t times u of t. Okay. All partial fraction decomposition questions or answers will always split up these roots, and then you'll use your inverse, your Laplace table, and just do the opposite. Go from the right-hand column back to the left-hand column. Okay, and this is our original answer. 120 minus sin 8 e to the negative at plus 48 e to the negative 6t. Obviously, this is a very complex answer. I ain't gonna lie. Right? You got a DC constant with 2 exponential decays at different levels. So there's probably multiple inductors in this circuit to cause these two things to happen. Okay. But this is how you would get the inverse Laplace transform. Come from this main equation, partial diffraction composition, and then you come out over here. Honestly, this problem will probably take about 2 pages of math, because between these here and here, there's a lot of steps in the middle, right? And then to get this final answer. Okay, but that's the distinct real roots. This is the easiest of our root sets. You can do the complex roots here, where you have a s plus 6 over s squared plus 6s plus 25. This s squared plus 6s plus 25 is a complex root. So if you use your quadratic equation, it's not going to come out nicely. It's going to be s plus 3 minus j4 and s plus 3 plus j4. Okay, you can still do your partial fraction decomposition. You'll get this number down here with a phase angle, and then you could do your inverse Laplace transform. It gets a little messy, but these two numbers could number crunch the cosine 4t minus 53.13 degrees, right? And it's basically the same thing over and over again. I've never seen this in my entire life, to be all honest, but it's something you should learn in the book just to know that it's there. Okay. Repeated real roots is kind of a similar idea, where you could get everything to a something divided by something plus another something plus a third root plus a fourth root, right? So you can see up here, you see how we're split into 1, 2, 3, 4 different roots. And then down here, this is our answer, 20 over s plus minus 400 over s plus 5 cubed, blah, blah, blah. And you could do a 1-by-1 conversion from the Laplace table and get your answer here, which looks abysmal, right? I don't know what monstrosity of a circuit caused this to happen, but I mean, I guess you could get that if it's really, really complicated, right? Lastly, you got repeated complex roots. This is the hardest one of all of them. And then you basically do your same partial fraction decomposition. You have 1, 2, 3, 4 roots. Find your variables on top. This is an answer. And then you could convert it to a bunch of sines and cosines all over the place, right? Again, I've never seen this in real life, but it is there as a tool in case you ever need it. Okay, so the main thing to know is just there's 4 roots. And then if you happen to have to do an inverse Laplace transform, you could go look at references to kind of do a step-by-step process to figure it out, right? But again, I think 9% of all electrical engineering, we don't do this. We stay in the frequency domain because that is the more important analysis tool. So for example, right here, let's say we have the initial function, 96 times s plus 5 over s plus 8 times s plus 6. We could get a lot of information from this. Let's say this is a voltage of the circuit. Okay, there's a couple really good questions. When is this voltage equal to 0? What frequency of S is required to make this whole circuit go to 0? Well, it's easy, as if S is -5, then we'll have 96 over 0 times 0 divided by a non-zero number. -5 into 8 is 3, -5 into 6 is +1, so it's 0. So what this tells me is as long as you set S equal to -5, or our frequency of our circuit is 5 hertz, this voltage flats to 0, which is very important to know. It's very important to know when the voltage goes to 0, and it's also equally important when the voltage goes to infinity. Because if any voltage or current goes to infinity, it's imminent, something's about to explode. So we want to stay away from that. We could do the same thing here. What function can we plug an S in to make this something divided by S? Well, obviously, if S is equal to -8, -8 plus 8 equals 0, so we go to infinity. So we put -8 in, we have something divided by 0 is S equals infinity. Okay, so when the frequency hits 8 or 6, this voltage shoots infinity. So what it tells me is I should probably stay away from 8 and 6, and I should watch out at 5 because that also goes to 0. Okay, so it's just nice to know those extremes of a circuit, and everything in the middle kind of falls between those extremes. If you have a 0 on one side and infinity on the other, between those two is going to ramp up. Okay, so a lot of information can be in a frequency setting can be given if we stay in the Laplace domain or the frequency domain. Okay, which is what I would suggest. Okay. Now, another really good idea that you need to know is initial and final values. So initial value means given this circuit, I don't know what happens at t equals 0. I really don't. Why? Because we're not in time domain. We're in frequency domain. So when a circuit starts and when it finishes at t equals infinity, or let's say like 5 days, that's sufficiently long time, what is the circuit going to do? Again, because we're in frequency domain, we have no clue. But there's a handy trick, so we don't have to go back to the time domain, because it's a giant pain in the butt to go from here to the time domain. I've showed you those 4 routes. That's too much work. It's called initial value theorem and final value theorem. Initial value theorem is within its frequency function, I can figure out what t equals 0 is without switching over to time domain. It's kind of like a little shortcut trick. Take your initial function f of s, multiply it by an extra s. So literally takes this number, tack on an s right here, and set limit s approaches infinity and tell me what I got. So notice we have our function. We're going to put an s in front of the 96 because it really says s times f of s. So this s goes to infinity right here. And then it's going to be 96 times s plus 5. What's s? What's infinity plus 5? This infinity. We're going to divide by s plus 8, which is infinity plus 8. So that's another infinity. And we're going to have infinity plus 6, which is another infinity. So if you remember, there's a special rule in calculus, like something like L'Hopital's rule or something, where you could cancel infinities because they're all approach infinity. And then you could cancel them out and get a regular number. So if I have 2 infinities on the top and 2 on the bottom, I could literally cancel out infinities. And then I just have a flat 96. So what this tells me is if I follow this rule, when the circuit turns on at t equals 0, at the very beginning, when I flip that switch, my initial voltage of the circuit is 96 volts. That's the real value it tells me. So whenever I have the circuit and I tell my friend, hey, turn it on, just make sure that I want you to know it's going to be at 96 volts right at the get-go. So wear your gloves, right? Another equally important is the final value theorem. What happens if I leave the circuit on for 5 days? Does it explode? Does it go to 0? Does it settle to a regular number? That's always important to know as well. Here, If we want to find t equals infinity or a very long time, again, like 5 days or a week, we could literally take the same function f of s, tack on a free random s in front, just like we did with the previous one. But this time set the limit of s approaches 0, and what do I get? Okay, so let's do it. So remember we have 96. We're going to put an s in front. So the s in front is immediately 0. We're going to have 96 times s plus 5, where s is 0. So we're going to have 96 times 5. On the bottom, we have 0 plus 8 and 0 plus 6. So we're going to divide by 8 times 6. So it doesn't matter what all these numbers are. Initially, we'll multiply by 0, so we're going to get 0 at the end of the day. So this circuit what these two theories tell me is whatever this circuit is, I don't know. The voltage starts at 36 when I turn it on. But eventually, when it reaches steady state, maybe in a few hours, when all the capacitor and inductors all steady out, the whole circuit is going to be 0. This voltage will be 0 volts. So what it tells me is when I turn on the circuit, it's going to do something, but eventually it's just going to bleed out and do nothing. It's basically going to be done. It's going to finish its task and then it'll settle out. Okay. So it's very handy for these two to know, are we going somewhere bad? So for example, if your final barrel theorem is this is equal to infinity, that's bad. That means something's going to explode if you set it on for too long. If it approaches 0, that just means the circuit won't last forever. It will always eventually die out. That's what this is telling me. Initial value is good because when I turn it on, it tells me what's my initial expected value, so I could prepare for safety reasons, and I know what to expect. Like when you turn it on, you're like, oh, this is 10 volts. Is it right or wrong? You're like, oh, I don't know. Right? It's good to know what's right or wrong when you turn it on, and that's what the math is for. Otherwise, you're just guessing randomly in the dark when you're flipping switches, which is bad because that's how you blow stuff up. Okay. So yeah, that's pretty much all I have for the LaPlace transforms. So just to summarize, because we did cover a lot today, I ain't gonna lie. Mathematically, your head's probably exploding. Okay. Just to make things easier. Remember, we have the LaPlace transform. You see it once, don't have to worry about it ever again, in my opinion. This is a Laplace transform that goes from a time domain to a frequency domain. Because remember, tasks are hard. It takes a hard RLC circuit and gets rid. So this transform takes a very hard RLC circuits and gets rid of second order differentials and turn it into algebra. Remember, exercise is literally just algebra. Okay. We could then either use the circuit as is for a frequency domain analysis, which is most of what the electrical engineering does. So that's why I put a star here. Or you can do inverse Laplace transform to go back to the time domain. Okay. Those are your two options where 9% of it's going to be the first one. Okay. Remember, the Laplace transform, there's two tables. The actual table for the swapping. So you have a transform table. And then you have an operation table, which will tell you the rules of if we integrate, do we divide by s and multiply by s, right? If we do a differential, what do we do? If there's a time shift, what do we do, right? So just put those two tables side by side when you're doing in your work until you memorize them. And that'll help you do these transforms. Okay. Don't sit there and try to do the math the hard way, right? Just use those tables, please. Makes life a lot easier. Okay. So that's all I have for today. We'll come back next week and we're going to see this new tool in action when we're actually doing some circuit analysis to take these previously impossible circuits and actually solve them within a reasonable amount of time. Okay. So thanks for showing up. I hope you guys have a good week. And as always, next week to start back up. So you guys have a good weekend. See you later.